Good morning, everybody. Good morning to our local representatives here that we have with us at Buitensteen in Gansbaai for a talk about Gerrie van Aswegen, structural geologist, who will take us through the stresses and strains that are involved in the rocks that we walk around and see here in Gansbaai. Thank you very much for joining us, and thank you very much for joining us on Zoom as well. Welcome to those people around the world that are now currently listening to us. The format will be, I will give a quick 101 geographical description for laypersons and non-geologists as to the setting for the Cape Fold Belt. And then Gerrie will take us further into the structural geology and start explaining things like shears and fractures and cracks and the reasons why and how to look for them, etc., etc., etc. A question that I often get asked here in Gansbaai by laypersons such as myself is, why is the Cape Fold Belt there? What are the Fold Mountains all about? Where are they? How did they get there? And so forth and so on. I'll try and sort of go back to Saldanian origin 900 million years ago and explain to current date within about 12 minutes, which is quite easy to do. It's only 900 million years. And the screen at the moment should reflect our Cape Fold Belt as it's lying at the moment. The orientation on the left-hand side of your screen is the westerly arm. In the center of that, we have a westerly arm sort of extending northwards, if you look up there to Vereinsdorp, and we have a easterly arm of the same fold belt stretching towards Kaberga or Port Elizabeth, with a syntaxis or a joint in the center. With the Cape Fold Belt lying there, we're going to discuss why it's lying there at the southern tip of Africa. And we need to do this in sort of three distinct portions. We need to sketch a canvas or create a canvas to paint the picture of words on that we're going to do. So we need to have a look at part one, where this whole thing was created. We had plates moving around on the surface of the earth, bumping into each other and creating mountains and getting weathered away and depositing sand and shale and mudstones and what have you. And if we can, just for the purpose of this discussion, then say that all of these erosions and planing off and construction of mountains and tectonics has already happened. We now land up with, let's assume a flat sort of surface, which is Malmesbury Shale, and in the center of that picture is a bluish rock, somewhat behind the guy's head there. That bluish rock is in actual fact the Malmesbury Shale, as it sticks out near Kogelbaai here in the Cape. That is the fabric on which we're going to base this whole story. So I'm going to move on quickly from here and just introduce the idea of plate tectonics, which was originally proposed by Alfred Wegener in 1912. He was laughed out of town with his idea. And it took our own Alex du Toit in the middle 1950s to take up this theorem and develop it and bring it to the point now where today it is a recognized theorem. It's accepted in geology, and it is a very solidly based theorem based in science now. We can accept now that the lithosphere, which is the sort of solid, and I use relative terms here, the solid rocks are floating or drifting on the asthenosphere, which is slightly more fluid, being magmatic. And on top of this lithosphere, we have plates of continental crust moving around. They move around for various different reasons, things like gravity work. We have subduction zones where one plate is moving underneath another plate into the asthenosphere and being remelted. We have mid-ocean ridges where spreading is taking place, basaltic lavas are rising up and beginning to move plates apart. We need to just, for the purpose of the discussion once again, accept that this is happening all the time. It is an inexorable process. It's very, very slow. I like to make the anecdotal comment that if Columbus or Chris, if he jumped off his boat today to declare the Americas found, he'd probably drown, because when he did it way back then, he jumped out into neck-deep water. And if he'd have done it today, that continent has moved already a little bit away from where he was. So he would have fallen into very deep water, and I doubt if his armor would have kept him above water. Having accepted that things move around, tectonic movement is real, and that continental crusts collide with each other and create mountains, which then get worn away, we can move on and have a look at the orientation of Gondwana land. Gondwana land came together in around 500 million years ago. sort of Cambrian, Precambrian timing. And this is just an orientation slide to show you that we were at the South Pole in the tip of Africa in those days, with South America nestled up against us, Antarctica on the other side, and behind Antarctica we had Australia, and India was also in there. So this was the consolidated view of Gondwana in sort of Cambrian, Precambrian times. Moving on from there, those plates have now moved together. They've created their mountains. They've created all sorts of funny things. And we get to the second part of this quick discussion around about how the fold belt got there. We talk about it in 4 different sequences. We talk about rifting. We talk about a deposition environment. We talk about compression and then the structural modification of the Cape Fold Belt. This is where Gerrie comes in, and he's given us a picture here of Stanford's Cove, just to indicate a little bit of shale lying within the quartzites on the top left-hand corner of that picture. He will then get into the ideas about how this starts to happen. If we talk about Gondwana in this cartoon as being the consolidated areas of light and darker brown, geology is never quite happy. So when Gondwana was consolidated, it immediately decided to start moving apart again. And you're looking at the time here as it's given itself about 100 million years to just take this decision. And the time factor is important because the time factor runs through the entire fabric of this discussion as being one of the main reasons for folding to happen. The consolidated plate then started to rift. There was tensional stress set up within that plate, and it rifted from the north right across the bottom tip of Africa there. And you can actually see a westerly part of that rift moving up the west coast of Africa with a syntaxis there, that joint where it joined onto the main rift. Now, all of the brown parts, and I'm using simplistic language here, will have now started to weather off, and it would be being deposited within that sea that was created in the rift. A rift is really just a huge crack. If you think about the East Coast rift, East Africa rift, that rift was invaded by the sea. I think it was the Paleotethys in those days, and created the Agulhas Sea, where you see it in blue at the moment. The brown bits were then eroding and weathering and depositing quartzites into that Agulhas Sea, in the base of the Agulhas Sea. So we have a cross section there, A to B. And if we have a look at that A to B in cartoon form again, and look at the time at about 400 million years ago, we noticed that Africa and the Falklands Plateau were moving apart. Think about that consolidated global picture that I gave you, and you will see maybe Falklands was moving away from Africa, maybe they're both moving away from each other. It doesn't really matter for this discussion. What's important is that rift in the dead center there, the tension being the stresses that are moving it apart, and the yellow part at the bottom underneath the blue of the Agulhas Sea is where those sandstones were being deposited. So they're being deposited in the bottom of the Agulhas Sea at that stage. If we sort of think about how things are deposited, we like to think that everything is nice and orderly, and it follows that everything's nice and flat at the bottom of that sea. Entirely not the situation. If we walk along the Hermanus path, we will see what we expect to see at the bottom of that sea, the Agulhas Sea, and I'm getting away from that word now because it's beginning to worry me. It's all nicely stratigraphically laid out or laid out in depositional patterns there. Now, this that you're looking at is in actual fact a very, very tiny part of the entire stratigraphy of that group of deposited sandstones that was in yellow in the previous slide, called the Cape Supergroup. And this part of the Cape Supergroup is the bit that lies right at the bottom of all of that stuff, and is the Peninsula Formation. So here's a very, very small section of that entire package made of stratigraphical column. And this small package just demonstrates the way that we would expect things to lie. Being geology, it doesn't lie in any way at all the way we expect it. But we see nice cross-bedding and a few little trough infalls here and what have you. Stratigraphically, if you drive between Pringle Bay and Betty's Bay, and thanks Dave Morant, and I've plagiarized a lot of the guys here sitting here, so they will recognize some of their material. for this photograph, where you can actually see thrusting coming in from the right-hand side from the south, and it has lifted up that whole plate, that whole depositional sequence, and you're getting a dip towards the sort of running from right to left. You're getting a dip as it is being lifted up. You can see the peninsular formation, which I've just spoken about, being at the bottom of that package. And then as the package goes up, you're getting shales, you're getting other formations deposited in a sequential fashion called the stratigraphy of that package, ending up probably with Overberg formation going up to Rickley. Rickley has already been removed from this photograph by weathering. But it just gives you an indication that on a very, very vast scale, that little yellow band at the bottom of the Agulhas Sea was in actual fact quite a substantial piece of deposition. 8 kilometers deep, maybe at some stages. Once again, we get to a nice situation where everything is now perfect, as it was in that first cartoon, where we have this nice flat depositional situation at the bottom of the sea. Geology then turns around and says, we can't have this situation. Everything's stable, we can't have it. So we're going to make the Falklands Plateau move back again. And the reason for this would be on the right-hand side of that Falklands Plateau cartoon, labeled B in this particular cartoon. We were sort of having a compressional force being exerted maybe by a subduction zone underneath the Falklands Plateau there. The net result is that the plateau is now moving back towards Africa. And you can see what's happening with that beautifully flat depositional environment at the bottom of the sea. Like a piece of dough on a table, as you exert force on it, it starts to rimple and it starts to fold and bend, and as it gets moved back towards Africa. Now, very often we will, and looking again at the time there, you can see the amount of time that's taken place. It's important maybe just to mention that things don't fold if things happen quickly. If things happen quickly, things break, they shear, they fracture, they do all those funny things. So time is an incredibly important value to this whole equation, where if there's given enough time, things will fold and flow over each other. Rocks will flow over each other with the time given. What then happens 50 million years later, the picture looks a little bit different. You can see the subduction zone there now going in underneath the plateau. You can see where those Cape Fold Mountains have been folded up and almost accreted onto this huge block of Falklands Plateau, which has been pushed up into some really impressive Andean type mountains there. Those are the Himalayas up there. They are really, really big. You're talking 16 kilometers above the mean sort of sea level at that stage, I believe. But amazingly, look at the Cape Fold Mountains. Those are where our mountains came from. They came from the base of that sea. They've been accreted onto a very much larger block. It has met Africa. And with that enormous weight in the center of your picture there, look what's happened on the left-hand side. The continental crust itself has started to sag, and that's where the basin was started to form for the Karoo Sea to fill. As that sea filled and the material was weathered off the top of Falklands, the Falklands Plateau, which is now the Falklands Mountain Range, that material covered over the Cape Fold Mountains, fortunately in one way, and started to fill up the Karoo Basin, amongst other places that it was busy filling up, because there's huge amounts of sediment that are being moved around. As the Falklands Plateau then got planed off and leveled off, the same forces of weathering started to wear away the Cape Fold Mountains. Now, it is possible here to see that the top part of those Cape Fold Mountains would also disappear into the Karoo Sea some stage there. And what we are left with currently is what we see. It's really just the dips in that yellow Cape Fold Mountain belt, the roots of what was an enormously impressive Cape Fold Mountain belt that was accreted onto there. If we look today at the mountain just behind us here in Gansbaai, we can see the folding that has taken place at very deep levels. Remember that we talked about burial of up to 8 kilometers. So things, when this folding and thrusting took place, were slightly different. Temperatures were much higher. They were probably in the order of 300 degrees. There is a little formula. But rocks would have behaved slightly differently than if they were at their current level, which is at sea level at 12 degrees Celsius. They were much hotter, and so they were allowed to move with the time. They were allowed to fold into what we see these days. You can see the thrusting came there from the right-hand side with the south. You will see examples of disharmonic and harmonic folding. Think about the open folding that you see towards the Hermanus Harbor, and where that previous picture was taken of the beds. That is fairly open folding. 30 kilometers away, you will see in the mountains at De Kop, the picture on your left-hand side, the intensely folded patterns that you can see there. And if you go even further afield, 400 kilometers away, you can see the different type of folding and the different examples of folding, almost recumbent and vertical folding that takes place in places like Meiringspoort. My favorite is Severbeekspoort out there towards Ladysmith. Some really, really beautiful folding. And all of that stuff is highly dramatic, but it has been allowed to do that by the amount of time that has been given to allow those rocks to flow over each other, as well as other factors such as there's a little bit of shale in there, in other words, mudstones and siltstones that have been deposited between and on top of those quartzites, and that has changed the nature of the way that things move. Gerrie will tell us more about how things break and how the forces are differently exerted. But in actual fact, time and temperature and pressure have allowed the folding. In cartoon form, going back to where we were, we had that basement of Malmesbury Group that I sort of indicated was some kind of canvas on which we can draw the picture that we've just talked about. Underneath that, we had, in the basement, we had these plutons of granite that were being intruded into that Malmesbury Group 500 million years ago. And we now look at things like the Pole Rock and what have you. Those are those red intrusions that are coming through the brown basement group there. In perfect world, we had the basement, the bottom of that sea, in which that purple lot was deposited. Those were the quartzites that were being deposited in the bottom of the Agulhas Sea. We had the thrusting, we had the Falklands move into Africa and then create those folded belts as they exist today. And you can see the Table Mountain Group, which is basically the Cape Supergroup being exposed there. And as I say, those are the roots of what we actually had before. If we move on to one of my favorite cartoons from John Compton's book, we're very proud of Table Mountain on the left-hand side there, which is about, I think, 1,000 meters of sandstones, and we say that is really wonderful to see. On the other side of the Cape Flats, we have the Hottentots Holland up there with also Table Mountain Group sandstones in there. In between the two of them, we have Malmesbury shales, which have been weathered away. We have expression of the Cape granite, such as the Pole Rock and a few other places that we can see around there. But have a look at what John proposes was the size of that stuff that was lying on the side of those Andean-type mountains on the Falklands. That has been weathered away, and those are quartzites. So those are very, very hard weathering-resistant quartzites. The amount of time that's necessary to take those away, to leave behind the roots that we are very proud of at the moment, you can see it's vast amounts of time, it's vast amounts of pressure, it's vast amounts of forces, and one of the bigger ones is gravity. It's not very strong, but it just carries on going forever. I'll leave you then with a thought, and this is where Gerrie's explanation is very useful. I'll leave you with the thought of part 3, and that is the breakup. Nothing is satisfied, nothing is happy in geology, so what does it do? It breaks it all up. Once the plate is nicely established, we have the breakup of Gondwana, all the plates moving apart once again, and we have this scenario where we understand now where on the globe all of those individual plates are, but it's taken 180 to 130 million years to get there. So once again, inexorable but very, very slow process. I will now hand over to Gerrie. Thank you very much, and I hope I've explained to some of us how the mountains got there. And Gerrie will take us through a lot of fine detail and then take us down onto the rocks to show us exactly how these things crack, break, fold, do whatever. Thank you.
The sediments before they folded, were they already solidified into rock?
Yes.
Soft sediments?
They would have been lithified to a greater degree. In other words, they would be competent rocks at that stage and recognized as rock. But there were temperature things and other things at play, but you can accept them in layman's terms as being rock then, yes.
We've just been talking about why do they call it the Table Mountain sandstone? Isn't there more quartzite than sandstone in there?
We actually look at the sandstone as being a generic term, as far as I can figure out from the literature that I've read. And remember, I come from a layman's point of view. The quartzites are the makeup of that sandstone. The quartzites are the things that have been.
Sorry, it's simply a question of terminology. We learned about sandstone, but actually, if you look at it, they are recrystallized, so they are actually quartzites. So they are quartzites, but we just refer to them as sandstone. Of course, you can see it's sandstone. Okay.
Sorry, can I ask a question? Well, it's
Yeah.
Spike McCarthy here from
Hi,
Joburg. Hi. Tell me, going back to du Toit's original description of these things, he wrote about a thing he called the Zamfara geosynclines. Zamfara geosyncline, which is he postulated a geosyncline that extends all the way from Patagonia through the Cape Fold Belt, across Antarctica and into Australia, and possibly even into New Zealand. How does that fit in with your idea of this rifting phase, this early rifting phase? Is that connected with this Zamfara geosyncline, or has the whole concept disappeared?
I have no idea.
Simple answer. Thank you.
Okay, let's go back to some basics. Look at the plate tectonics driving forces, some brittle ductile folding, and so on. Wegener, being a meteorologist, had proposed tidal forces and centrifugal forces as the main driving mechanisms for continental drift. But if you lived through Gansbaai in July, you may think it was the wind. You may see how the monsoons are pushing India underneath the Himalayas there. Okay. So what are the driving forces? Gravity, mid-ocean ridge, gravity away from the mid-ocean ridge, and gravity again. So there's gravity on the left-hand side, convergent, gravity divergent. It's like a conveyor belt, these plate motions. And we also notice that there's some differential motion along those conveyor belts. We'll see the oceanic crust is moving faster than the mantle below. So we need some pushing on top of the conveyor belt and some pulling on the left. So there we go. So the pushing comes from the mid-ocean ridge by gravity, and the pulling comes from the subduction zone by gravity. From Wikipedia, we can read this slab pull is a geophysical mechanism whereby the cooling and subsequent densification of subduction tectonic plates produces a downward force along the rest of the plate, and that was considered the main force for these oceanic plates moving apart. However, I don't like it because rocks are weak and flawed. So they are very weak in tension. For that slab to pull the whole ocean towards it, I don't like that theory. So that could be some questions. Okay, gravitational flow to form the Cape Fold Belt. Heraclitus was I'm not sure whether I pronounced the name correctly, was a Greek philosopher, and he said everything flows. Pantare, everything flows. So to quantify the flow, we must look at things like shear, the shear modulus, and viscosity. Once you have the shear, look at stress and strain rate, you get to viscosity. You can see the sandstone slab has a viscosity of 10 to the minus 8 Pascal seconds. Then there's an interesting one called relaxation time. If you load a sample to some level of stress and then hold the load and allow the sample to relax, there's some time associated with that. And the relaxation time turns out to be simply the viscosity divided by rigidity or shear modulus. So if you have relaxation time and you have observation time, you can define the Deborah number. Deborah number is simply relaxation time divided by observation time. The concept was presented by Marcus Reinier, and he's after dinner speech to the 4th International Congress of Rheology at Brown University in 1963. He said, the prophetess Deborah, who in the book of Judges, that will be a long time before our Greek philosopher, proclaimed that the mountains flowed before the Lord. In his speech, he said, Deborah knew two things. First, that the mountains flow, and as everything flows. But secondly, that they flowed before the Lord and not before man, before the simple reason that man in his short lifetime cannot see them flowing, while the time of observation of God is infinite. So there's relaxation time. So if you have observation time is very long, very, very, very long, and the relaxation time is short, the fluid-like behavior can be expected. So if we really think in terms of 200 million years for orogeny, then really that observation time is very large, and we should expect flow, ductile flow. Our mountains should have been deformed in a ductile manner like that. Those would be typical ductile folds. And there's some relatively quick ductile deformation of a slab of marble or something, and it's simply under its own weight is folding. However, when we go and look at the rocks, we see that the folding is largely brittle. That's our classic picture from Silver-Export. There's the bedding, there's some fractures, some with the bedding. And there's those red little vertical lines is some ductile fabric. Bedding spurt folding, more folding, and faults. There's a cedar bag formation, and above that we have these crinkle cut folds. Stress stacking is considered an important way of thickening the sequence. I will have a picture of that in a while. So a lot of faulting there. Remember that faulting, that's important. And then we get to overfolding. You will see in this map, there are some symbols down to the right where the symbols actually show overfolding. And we use to recognize overfolding, one way to look at it is using crossbedding. There's crossbedding the right way up. There's crossbedding the wrong way up, upside down. Crossbedding at a gallas, upside down. So we know the strata is upside down. And then on top of that, you'd add some deformation and it becomes quite complicated. There's some thrust stacking, I think, at gallas. You can see the folding there. You can see that bed coming from left top to the right bottom is thicker at the bottom because of thrust stacking. This is the mountain behind us here, Denefontein Berg it's called. Maybe if we look along the fold axis, the folding may not be so disharmonic as some people are claiming in this room as we speak. Okay. Then brittle against ductile. There's some story about why is it brittle, and there's some explanation by Fagereng. So how long did it take? It's concluded that the main phase of the Cape Fold Belt was around 253, but it doesn't say how long it took. There's some reason to believe that these orogenies, the main phases are not so long, maybe 8 million years. And our rocks were cool, lowermost greenschist phase is 300 degrees centigrade. So the rocks probably deformed relatively fast and they were cool. So it turns out that our mountains never flowed the way Deborah envisioned, since they were too cool and the time was too short. And in the top left of that picture, you will see two zones that I added. And that gives you more or less the time and the temperature at which these rocks deformed. And you see they're not in the zone of ductile deformation. On top of that, the deformation was associated with faulting, thrusting. Brittle faults do behave in a stick-slip fashion. So maybe we can consider these deformations as millions of short actions, quick deformations. And so we do not get much ductile deformation. Fat belts, fold and thrust belts. This is a very typical fold and thrust belt. And if we look at the interpretation from geophysics, we see a picture which very much like a fold and thrust belt, as we saw before. And because the rocks are behaved in a relatively brittle fashion, you are given the license now to model it in software that normally is used by the rock mechanics. In this case, Rudy Kasten built a flak model to mimic what we see on the left. On the right is the flak model. And you see in this flak model, those black lines indicate the likely orientations of thrust planes. So the modeling kind of agrees with the observation in this case. At Stanford's Cove, we see, however, a lot of ductile deformation. We don't know the lithology. We don't know the stratigraphy. There's some shale there, and I don't know what it is. There's some quartz veins which are folded in a penetrative actual planar with actual planar foliation. And then on top of that, there's some layers that are deformed brittly. So Stanford's Cove is on the bottom left of this picture, and the yellow circle there indicates where we sit at the moment. That's a drone image of Stanford's Cove. And there's some sketching on top of that. There's the white lines are just simply following S0, I believe. And the purple line down the bottom is a fault which separates a zone of vertical orientation of bedding from a zone with an area to the south where the bedding is dipping gently to the south. And that's what it looks like. And we'll see it in a few minutes. And that picture you've already seen. And there's those ductile type deformation. On the left there, you see folding with ductile matrix, and then two pictures of the shale deformed in a very much a ductile fashion. And to add a little bit of science, Mike and I went and measured the orientations of those fold axes and plotted them, and they're all trending to the northwest. Some more folds at Stanford's Cove. You can see there. It's quite difficult. Actually, it's easier to see them in the photograph than seeing them in the field. There's another one there. And really, you struggle to see them. But once you have a photograph and you sit back and you have a glass of wine, you start seeing these structures. Okay. And to interpret what happened there, I really don't know. But maybe this kind of explanation is valid. There on the left is the fault that separates the dipping, shallowly dipping strata to the south. Then this ductile shear zone, and then the open folds to the right. But anyone's guess. Actually, Stanford's Cove is an MSc waiting. Just get some funding and get some done. On top of that is brittle deformation. These are quite interesting. You look at them and you look at this picture, you say, it looks like bedding dipping to the left. But actually it's not. The bedding is vertical. Strata is vertical in this picture. And those flat line discontinuities are extension fractures. There's more of it. And there is proof that these are extension fractures. Extension fractures have this characteristics of forming these fractographic striations on them. This is typical of an extension fracture. Quite often, a fracture would form in extension form, and then it would shear afterwards and destroy all this evidence. So you're lucky to actually see the evidence of the extension fracturing on these rocks. There's the picture on the left, the same, very, very much the same rock. You'll see the evidence of extension fracturing on the right there. There's another interesting feature. This is a bit to the east, to the west of Stanford's Cove. We'll be going in that area as well, near Raaswater. And that's bedding and fractures in between two beds. And what we have here is part of a fold. It's one limb of a fold. And along the fold, we have flexural slip. So the two beds are sheared relative to each other, and then you have these classic en-echelon extension fractures between them. So it means that these extension fractures formed during the late phase of actual folding. So it's very brittle. This is the Stanford's Cove area again. And it's now looking towards the sea. And you see the bedding, the ductile shearing in the shales, and these quartzite beds in between all have these fractures like that. There's an extension fracture dipping like that, similar to the ones I just shown you. And if you use your imagination, you can even see some fractographic striations there, proving that these are extension fractures. Okay. Then the late phase of extension fractures in the area here, there's a photograph at Stanford's Cove showing some classic pattern of en-echelon fractures along a shear zone there. So we're looking at some late brittle shearing. It's a prominent feature of Gansbaai and Hermanus, and also wider. There are conjugate sets, generally steeply dipping, cuts older folds and foliations, but older than the overlying Daarstorp group. So there's a gallas, but zoomed in a bit and zoomed in a bit. And there you see from top right to bottom left is the bedding is 0, and across striking northeast southwest is this very penetrative set of extension fractures. This is simply a Google Earth picture. Danger point, just go back, that's danger point, not far from us. There you can see some open folding, and you can see this extension fractures across. And Stanford's Cove, there again, you have bedding, very steeply dipping bedding, and the extension fractures. And there's even over there some displacement along a fault parallel. You can see there displacement along a fault parallel to these extension fractures. So they are not simply joints; they are actual, real fractures, extension fractures. And it's quite wide. This is a similar set of structures mapped near Port Elizabeth. This is at Hermanus, and I want to point out that some of these extension fractures are actually rotated. That's an interesting feature which I have a big song and dance about. So this is now where the second leg of our field trip is going, to this area, and I call it the Raaswater shear zone simply because the street Raaswater stops right there, and the structures are down there. The drone image is better. You can see bedding, very much vertical, steeply dipping. That's south, that's northeast, and the extension fractures cutting across there. And then, if you go down into that gully, and this is where we're going, we can step down into the gully and you look in that direction. Now my mouse is actually working. Why? You can actually, you look in that direction, you see this beautiful set of fractures. Main fracture along there, then a second set joining asymptotically, and between them a third set, and between them a fourth set. Whole series of extension fractures. This is called scale invariance, where you have a whole series of structures which all look alike. And then on top of that, we have some extension fractures which are rotated, are bent. Now, this is a very late stage of fracturing. In the previous presentation I did online, I had a long, big song and dance about these rotated or folded or deformed. It appears to be deformed, but actually what happens, the extension fracture simply follows the sigma 1, sigma 2 plane. the stress trajectory. The stress trajectory is not straight. In a shear zone, it actually curves. And it wants to be, if you have slightly tensional shearing, your sigma 1 curve, sigma 1 trajectory wants to be parallel to the shear zone. But inside the block which is being sheared, the extension, the sigma 1 trajectory curves. And then when the fracture happens, it simply follows. So the extension fracture is a fossil imprint of the orientation of the sigma 1 stress trajectory at the time of happening. So this is like a fossil trace. And there's just more proof that these structures are extension fractures. There is some fractographic striations on them. So, in conclusion, Gansbaai area is rich in interesting geology. Structural geology, largely unexplained, I must say. The Table Mountain Sandstone, actually, there's a better name for that. Stratigraphy, I have no idea. We don't know what's going on. We don't know how to name that shale band. And then the younger strata are well described by likes of Jean Malan and Haley Cawthorpe. So they can tell you everything about what happens on top, but us guys trying to look at the sandstone and coal sites below, we don't know. I can open another one for recent. Let's look at, there's that shear zone we're going to look at. You can see, interesting, the extension fractures on the one side of the main zone. Extension fractures approach the main zone asymptotically in that fashion. On the other side is the opposite. And in ductile deformation, this pattern would suggest right hand down, but in brittle terminology and brittle failure, this pattern is left hand down, not right hand down. Okay. I think this is where I should stop and we can have some discussion.
Thank you very much, Gerrie. If you guys in there are having any questions, if they can just come up to the mic so that we, the listeners, can also hear what the question is.
I think the mic is in here. Sure.
Gerrie, I'm just going to kick off with a question from long ago. If you could take yourself back to Hartbeesfontein gold mine, and the fact that we were the only mine doing sub-level caving there. What role did extension fractures in your mind play in us doing stress relief at the face?
I think when you do that kind of caving, you move the fractures, or you move the stress ahead of the face, further ahead of the face, and then it forms extension fractures further ahead of the face than before. So if you're basically closing the stope quickly instead of trying to keep it open, and because of that you are pushing the stress further ahead of the face. And because of that you have extension fractures further ahead of the face. In that way you actually soften the face area. So in that way you could make it safer.
So back with jam crash. Thank you very much, Gerrie. That's exactly what we had in mind. Right, any questions from our audience across the seas? There's somebody in the chat column says, hi Gerrie, could the shallow dipping fractures around the middle of your talk, slide 30, be related to fold cleavage? This is regards from Mark. Good art.
Yeah. No, the flat dipping bedding, for example, the only place we see flat dipping bedding here is at Stanford's Cove, and that's to the south of the shear zone. That is simply one part of a fold, which is open folding. So with open folding, we have these shallow dipping bedding on one side of the fault, while across the fault at Stanford's Cove, things change dramatically and the strata is vertical. So there we have tight folding and the strata is vertical. So no, I would say it's simply very much easy, simple explanation. It's simply part of open folding. That's why the strata is dipping shallowly. Maybe he refers to the shallow fractures in the brittle fractures in the steep dipping bedding. In that case, that's again simply extension fractures formed in a brittle zone because of movement on either side, shearing on either side, as I've shown here. Yeah. Let me show you a view. Okay. Good. View presentation. There. In this case, I have shearing with flat dipping extension fractures. Just forget for a moment about the curvature, but that's essentially the way these flat dipping extension fractures happen.
Okay, then maybe I misunderstood you, but I sort of heard a little bit of a difference in opinion in terms of the time available. You sort of said, look, it takes much less time.
In this particular instance, the picture we're looking at, those fractures happened within milliseconds. These are dynamic features. So those fractures, in the late phase of the Table Mountain orogeny, I don't know, at some stage when things started drifting apart, at some stage they had some, because these are all transtensional shears. Every time I see them, it's all transtensional. So at some late stage of relaxation or opening, I don't know, I have no idea. I just know it's late in terms of Table Mountains group, but it's older than the overlying rocks, the young stuff that Jean will talk about, knows about. So it's late, but when it happened, when the picture you look at, when those fractures formed, that took milliseconds.
Okay, then there's a couple of statements here made by Elzavita. She says, I think this is the opposite sense of shear. I'm not sure, but look at the
No, she's
drag.
wrong. She's wrong.
just finish. Or rather the shear changing direction, or rather the shear was changing direction, but she said look at the drag and says first open the fractures and then drag them.
No. This is exactly.
Well, talk to her, and if she can maybe unmute herself and talk about it a bit. Elzavita, you want to join us with your mic?
Okay, thank you. No, I was just looking at the drag of the tips of the fractures, and somehow intuitively it feels like it was an opposite shear. But I understand that to open extension fractures, you do need to shear them in the direction that is shown at the picture right now. So that is what causes me confusion. So was that sense of shear changing?
No,
Kind of
not at all. I know I've been through this for a couple of years now, and we all went to university and we all studied structural geology and we all looked at folds and fractures and shear zones. Shear zones is a big thing. And we got this picture. And if I take away those arrows, it's psychological. You just look at the picture and you know it is left hand down. But in fact, in this particular case, it's right hand down. Because we have to breach that psychological barrier of looking at every pattern like this and believe it's always ductile. It's not. In this particular case, it's not.
Okay, thank you. Thanks.
Hermanus, you keep unmuting. Any question from you? We can't hear you. Okay, guys, are we about to wrap up here? You guys can go out on a field trip now.
Yeah, I think we're done. I didn't think I would get through all the slides, but I did. So, yeah.
Yeah, thanks very much, Henny. We will wrap it up now and then move down to the rocks to go and give Gerrie a hard time down there where he's most comfortable.
Thank you
And
guys
ask
for
him
giving
some
us
more
a very
questions we
interesting
can't
talk.
answer. But thank you very much.